The classic example to introduce Bayes' theorem involves testing for a rare disease. And this is commonly held up to demonstrate how humans are not good at thinking probabilistically, and how Bayes' rule can run contrary to what our intuitions would give. And I'll be the first to admit there are few things more fun than counterintuitive results in math, but I do think that making this the first example that someone sees of Bayes' rule runs the risk of insinuating that the rule itself is counterintuitive. But quite to the contrary, one of the most valuable things about this rule is that in most cases it captures what human intuition seems to do naturally. What's more, as I'll explain in just a minute, I think Bayes' rule has been falsely accused here, and the real culprit for why this example is counterintuitive lies elsewhere. The setup is that there's a rare fatal disease that affects 1 in 1,000 people, and there's a test for detecting it. The test is really good. If you have the disease, the test will definitively 100% tell you that you have it. If you don't, the test will, with 99% accuracy, tell you that you do not have it. In other words, 1 in 100 healthy people get a false positive. So imagine yourself taking the test and getting a positive result back. How worried should you feel? Quite often, the reaction is that with a test that has 99% accuracy, you should be all but certain that that positive result is a death sentence. And I wonder how true that would remain if you just rephrase the question to emphasize that you're updating a prior belief. You initially give a 1 in 1,000 chance to the possibility that you have a disease. Then you take a test with a 1 in 100 false positive rate, and it gives you a positive result. Now, what are the chances that you give to having the disease? In the last video, we were visualizing the space of all possibilities as this 1 by 1 square, dividing it horizontally to represent our prior beliefs. And that same method would work fine for us, but the fact that we initially only give a 1 in 1,000 chance to having the disease would be represented with an exceedingly thin upper slice, sort of difficult to see. But with this example, we can actually be a lot more concrete. Picture the space of possibilities as 1,000 specific individuals, only one of whom has the disease, and 999 of whom do not. So how does receiving that positive test result restrict this space of possibilities? Well, that one poor person with the disease definitively gets a positive result. And if you're one of the 999 who do not, the probability of a positive test result is 1%. So about 10 of the healthy people will get false positives. So all you really know from that positive result is that you are one of these 11 people, only one of whom has the disease. This gives a 1 in 11 chance, or about 9%, that you have the disease. Or said a little differently, the effect of a positive test result on your prior belief, which started off as 0.1%, is to increase it by a factor of 90. At first, this might seem like a depressing result for medical test designers, where even a 99% accurate test can leave a person with a positive result 91% sure that the test is wrong. But on the other hand, it would be unreasonable to expect that a test with a 1 in 100 false positive rate should increase your prior belief by anything more than a factor of 100. When a prior starts so very, very low, it takes a seriously significant amount of evidence to change it. We might as well take this opportunity to get a little more practice for what the formula for Bayes' rule actually looks like. In this case, we want the probability of being sick given a positive test result. This is the probability of being sick and getting that result, divided by the total probability of a positive result. The top part there breaks apart as the prior of being sick, given no new information, times the probability of a positive result given that you're sick. Because the test works perfectly on diseased patients, that top is just the same as the prior, which is 1 in 1,000. As usual, that denominator breaks into two different cases, the first of which is having the disease and getting the positive result, which we just saw is 1 in 1,000. And the second case is not having the disease, probability 999 out of 1,000, times the probability of getting a positive result anyway, which is 1%. And indeed, if you compute this fraction, you will get 9%, like we saw before. The thing is, once you actually think about the group of 1,000 individuals, the result seems straightforward, maybe even obvious. But to understand the relationship between our intuitions and the mechanics of probability, It's worth asking why, at first glance, it seems so very counterintuitive that when you receive a positive result from a test with 99% accuracy, you should doubt that it's correct. Where exactly do math and intuition disagree here? My own suspicion is that Bayes' rule is not to blame, that the formula remains largely loyal to how our gut updates prior beliefs. Instead, I doubt that we can really program our own prior beliefs just by being told the appropriate numbers. There's a difference between hearing that 1 in 1,000 people have a disease and actually having the deep-to-your-bones instinct prior belief of 0.1%. Instead, we focus empathetically on that one visceral case of the disease. And empathy turns into irrationality as that little hypochondriac inside all of our heads overweights the possibility of being that one person. In other words, the prior in our intuitions is, irrationally, more than 0.1%. To illustrate what I mean, consider a less medical example. Imagine a hypothetical world where 1 in every 1,000 people have mind-reading powers. And imagine that I claim I can read your mind. And to prove it, I'll have you randomly generate some number between 1 and 100 and to concentrate on it really deeply. And then, in this scenario, let's say I make a claim about your number and it's correct. Would you believe that I can legitimately read your mind, or that I just lucked out? And what chances would you place on it? Notice, the probabilities here are all identical to the medical example. The prior should be 1 in 1,000, and the chances of me correctly guessing your number without having any special powers are only 1 in 100. But somehow, if you really picture yourself in this situation, it's easier to say, yeah, you probably got lucky, than it is to look at a medical test and say, sure, this test with a 99% accuracy is telling me that I have a deadly disease, but it's probably mistaken. In the real world, we place an incredibly low prior on people having mind-reading powers, dramatically lower than 1 in 1,000. And we place an unjustifiably high prior on having certain diseases. And I'm not comfortable assuming that those priors change just by being told the numbers, even in a hypothetical. Some survival instinct part of the brain says, I don't care about your statistics. Knowing my luck, I probably am that one sick person in 1,000. So in some sense, rather than serving as an illustration for how counterintuitive Bayes' rule is, I think this example can be viewed as a clever way to measure how much we disbelieve statistics, using the fact that Bayes' rule is an honest reflection of how we update our core beliefs. Either way, though, whether you think the reason it's counterintuitive is because of Bayes' rule, or because of our inability to program our own priors just by being told numbers, the main takeaway here is that the whole example becomes a lot more intuitive when you actually picture the space of possibilities. And this is common among apparent paradoxes in probability. Results that seem to run completely against our snap judgments can almost always be put in alignment just by picturing what's really going on. Next up, with the foundation of Bayes' rule under our belts, I'll be getting into Bayesian networks. See you there!